We're going to continue talking about electrochemistry today. And of course, we introduced this concept that we can use a chemical reaction to generate electricity. And what we're going to talk about today, honestly, not a ton of math today, really. In fact, might not be any math in what we're going to do on the board or anything. But we're going to do some more concepts type things today. Section 2 in chapter 20, titled batteries. Okay. And that's really all a battery is. So if we have just this little battery right here, this is a chemical reaction. That's what is generating the electricity here. We have two different half reactions of a redox process, and then we separate it, and by separating it, we make it so that the only way that the reaction can happen is by using that electricity. We force those electrons to go through a path that we want in order to get, well, the power that we want. So there are several different types of batteries, and we're going to talk about a bunch of them. But when we talk about them, one thing that you will notice is we will call them cells quite a bit. We mentioned, when we drew up the initial one with the zinc and the carbon, and we separated them between the two, and we said, okay, this is a voltaic cell. And that's the name that it was given, and that name still has stuck around quite a bit, even though we do call them batteries. As the book says, up until fairly recently, for well over 100 years, the most commonly used voltaic cell is called the zinc carbon dry cell. Now we call it a dry cell because it's not actually in aqueous solution. Okay? The example that we drew up on the board, we had those two beakers and they had solution. It was a very wet cell. This dry cell, instead of being immersed in water, some sort of solution, it's actually more of a paste. Okay? So there still has to be some liquid in there, but it's not enough to really consider this a wet application. It is, that's why we call it a dry cell. So, and it kind of breaks it down on page 718, sort of what the inside of one of these dry cells looks like. We have basically zinc and manganese. Okay? This is what we're actually going to put inside this battery. Okay? And I mean, there's a few other things talked about, the ammonium chloride and things like that. We put these things so that they can react. And we put them inside a zinc shell. This zinc shell acts as the anode. So that's where oxidation is happening. That's where the electrons are going to be coming from. The cathode is where the reduction is, and that's actually carbon, okay, graphite. We've got, remember, this graphite rod in the center. Now, the interesting thing is, the graphite actually isn't part of the redox reaction. Okay? It is still the cathode, but it really just serves as a conductor of electricity. Okay? You can see it gives us the reduction half reaction, and it's probably one of the more complicated half reactions that you'll ever see, at least in this class, because we've got the ammonium ions, the manganese dioxide, and then it's changing to manganese trioxide with just ammonia and water. So obviously within the structure, we have to separate these two things. We have to have, well, they call them spacers, to separate the two half reactions, because if you mix everything together, well, everything's going to react before the electrons are put to use in our circuit that we use the battery for. So, nowadays, instead of using zinc carbon, typically we use what are called alkaline batteries. Okay? So this is an example of a zinc carbon battery. Notice it's fairly large. The biggest advantage to alkaline, and pull these out again here, we can make them smaller. Okay? So we have our zinc carbon, our alkaline. That is the biggest advantage to our alkaline batteries. Now, remember when we talked about acids and bases, another word for a basic condition is alkaline condition. So that's actually where the name alkaline batteries come from. We use a basic condition inside there with the paste in order to, facilitate the transfer of electrons. Remember, acids and bases, because they form ions in solution, they conduct electricity, which means we've got electrons moving. So we use the alkaline solution to do that. We still do use zinc and this manganese dioxide, but because we're getting rid of the, this big carbon portion that we need in the zinc carbon battery, we can make them smaller. Now this one, you can make a smaller zinc carbon battery, but you're not going to get really small batteries with the zinc carbon. So, the next example that the book gives is called a silver battery. Sometimes these are known as button batteries because they are small and thin, more like a button that you would find on clothing. So these are really useful for things like watches, hearing aids, and things like that. You get these really small batteries. Now we call them silver batteries because they use silver oxide. we use silver oxide and zinc still. Zinc is, oh, it's a pretty good component for a battery. But anyway, so we've got the silver, the button batteries. Okay? So we often find them in like watches and things like that. So now, when we talk about batteries, we have to break them into two different categories, two very broad categories, and all of the other categories that we've talked about, the zinc carbon, the alkaline, all of that, they will fall into one of these two categories, either primary batteries or secondary batteries. So a primary battery is, well, it's one like this, okay? Once you use up all of this battery, you call it dead, and you throw it away. The redox reaction in this, while yes, it can be reversed, it's pretty difficult to reverse it. So with primary batteries, you use them up and throw them away. Secondary batteries, however, are just the opposite. Okay? The reaction is fairly easy to reverse. And so we can do what's called recharging. So any battery that the reaction can go backwards very easily is a secondary battery or rechargeable. Okay, we have to use different materials in order to do that. One very common one is, well, this was one of the very first ones that was widely used, NiCad, nickel cadmium. That redox reaction is actually pretty easy to reverse. And so we have these rechargeable batteries. Instead of throwing them away, you put them in the charger. It actually forces the electrons to go backwards, and that reverses the chemical reaction. Kind of interesting to think that when you have a battery that's recharging, you are physically making new components. You know, it keeps going back and forth. So when you're using the battery, you get this reaction going one way. When you're recharging it, it's going the other way. So there are several other examples of secondary batteries. By the way, we also call secondary batteries storage batteries. Okay. Not sure where that name really comes from, but just so you know, secondary batteries are often called storage batteries as well. The first one that it talks about is the one that you would find in a traditional car. So not an electric car, we'll get to those in a minute, but just a normal, traditional gasoline-powered car. That one is going to be a lead-acid battery. We call it lead-acid because the reaction is between lead and sulfuric acid. So we have these plates of lead, and we have we have a sulfuric acid solution that's in there as well. The sulfuric acid serves two functions. It is an acid, so it can serve as the electrolyte, but as you discharge this car battery, it actually uses up the sulfuric acid to create lead sulfate. So if the battery ever runs out of sulfuric acid, it will be dead. It's not going to work. You have to put more sulfuric acid in it. In fact, older batteries, you used to be able to do that yourself. Modern batteries, they're all sealed up. You have to send them off for recycling. So, but these are storage batteries or secondary batteries, which means they can be recharged. Okay? They can be recharged. In fact, during normal car operations, the battery gets recharged as you're driving. As the engine runs, the battery will be recharged. If, however, that is not functioning properly, your battery could go dead. At that point, you might, we call it giving the car a jump start. And that's where you get another car with a good battery and connect them with cables so that there is, charge from that battery coming into the car, which forces this reaction backwards, and we get more of the electrolyte, the sulfuric acid, being generated. So in this case, we go from lead sulfate to sulfuric acid. So, we use these type of batteries to, for gasoline-powered engines because, when it's working properly, it gives a lot of initial power. When you turn the key to start that engine, you're using the battery to turn the actual crankshaft and moving all the pistons up and down until it gets the gasoline flowing and we start to get the gasoline pushing the pistons, which keeps the motor going. But until then, you're using the battery to actually turn the engine. So, a couple of other advantages: they last several years. With you can use them over and over and over on a daily basis for several years. I believe most car batteries have a warranty of at least 5 to 10 years, just kind of depending. But anyway, also, they work at lower temperatures than some other batteries. Remember, temperature can affect how a reaction happens. So if you have a low temperature, that can affect the amount of power you're getting because it's going to slow that reaction down. Now, even lead acid batteries are affected by the cold. You're more likely to have your battery fail in cold weather, but the lead acid battery is a little bit more resilient than a lot of other options. So, however, like I said, we don't use that for electric cars. And the biggest reason is, if you have ever had to change a car battery, they are very heavy. They are incredibly heavy. Lead is not a light metal. So the problem is to have enough lead acid batteries to make a car, move just off of that power, it would be so heavy that your range would be almost nothing. And it's just not useful for that. So instead, we needed to find a lighter material. And remember, if we look at the periodic table, so we've got lead here, so it's down at the bottom, very big atom, very heavy. We decided we wanted to work with something a little bit lighter, lithium. Okay? Lithium is actually the lightest metal on the periodic table. Okay? You can have an entire mole of lithium at just under 7 grams instead of an entire mole of lead at 207 grams. So that's a 200 gram per mole savings. There's actually another really good reason why we wanted to use lithium. If we look back to our standard reduction potentials, lithium has the absolute lowest reduction potential at -3 and some change. Okay? So not only is lithium very light, but it is very, very willing to give up its electrons. So that makes it a great choice. Now, that makes it seem sort of like it was really obvious, like, oh, hey, let's use lithium. But the fact is, recently, the inventor of the lithium-ion battery was awarded a Nobel Prize. And it was a well-deserved prize because, honestly, our world is rapidly shifting towards these lithium-ion batteries. There's a lithium-ion battery in here. There's a lithium-ion battery in my computer. Just about any modern technology device is going to use a lithium battery. And it's for those reasons that we talked about. Okay? It's light. Okay? If you've got your cell phone, you want it to be light enough that you can carry it around. Okay? So we want a light battery that's going to provide a lot of power. Okay? Lithium is the answer to that. Okay? As it says, if you compare lithium and zinc, because we've been using zinc for a lot of these other batteries, not only is it going to be lighter, but because of the differences in the oxidation, the reduction potentials, both of them are going to be oxidized, but the reduction potential for zinc is -0.762, whereas lithium is -3.04. So if you have the exact conditions, but one of them is using zinc and one of them is using lithium, you can get about 2.3 volts more from the lithium, and it's going to be lighter. So, depending on what you pair this lithium with, it can be either a primary or a secondary battery. So lithium is okay to be recharged, but sometimes the other material that you're working with isn't. We are starting to see lithium replace the silver batteries. So now you can get lithium-based button batteries. Okay. But if you are using a modern rechargeable battery, there is a very, very high probability that it is a lithium-based battery. If you ever are riding in an electric car That is definitely using lithium batteries because otherwise the car would just be too heavy. Anyway, the last type of battery that we want to talk about, it's called a fuel cell. Fuel cell. And it starts out by talking about, okay, so we've got hydrogen, and we know that we can take hydrogen, react it with oxygen. Okay? And we're going to get water. We can balance that there. So, the problem is, that's a combustion reaction. And this, if you react hydrogen and oxygen together, typically what's going to happen is something's going to blow up. But we've actually been able to realize that, okay, well, if we do this properly, this is redox. Okay. So if we can get this to, work the way you would like it to, we can generate electricity with this reaction. Now, the reason why it's called a fuel cell, so this battery has a certain amount of chemicals in it. You put them in there, that's what it has. Battery in here. Okay, so yeah, it's rechargeable, but you've got a certain amount of chemical energy, and once it's dead, you have to spend time recharging it. A fuel cell is a little bit different because instead of saying, okay, we've got this amount, and when it's done, we just have to get rid of it or recharge it, we just give it more fuel. Okay? A fuel cell can last as long as you keep giving it fuel. And so that's one advantage, is that, instead of if you have a lithium battery in a car, okay, well, once you've used all of that energy, you have to plug it back in. Okay? And that can take a long time, hours to recharge. In a fuel cell, if you were to put a fuel cell in a car, you've got your tank of hydrogen. Now there's plenty of oxygen in the air, so you can just use that. Or you can have a tank of oxygen. That works too. But you've got these, and if you run out, well, you put more in, and you're good to go. It's not a long recharging process. So, fuel cells have actually, the idea for them has been around for quite a while. The first one was demonstrated in 1839. So it's been around for almost 200 years at this point. But they didn't really start to gain popularity until the space program. So obviously, if you're going to have astronauts in space, they need electricity to power their ships and equipment and things like that. And they need water. Okay? Humans have to have water. That's just a fact. Well, the engineers designing these spacecraft said, okay, well, water is really, really heavy to send up. And so are batteries and creating electricity and things like that. This fuel cell solves both of those problems. Okay? So we're going to generate electricity, and we're going to generate our drinking water. So that is typically how we generate electricity for a lot of these spaceships. Obviously, if it's going to be a long-term staying in space type thing, like the space station, then we'll also look at things like solar panels. But when the space shuttle was running, it used electricity from a fuel cell that generated drinking water as well. So, anyway, the book breaks down a couple of different physical ways we can do this. I'm not that concerned that you know the actual physical construction. So, anyway, now the last part of this section sort of skips away from batteries. So instead of discussing batteries, we're going to talk corrosion. So it's pretty common knowledge that if you have something made of iron, if you leave it outside, there's a good chance it's going to rust. That is a redox reaction. It is also what we call corrosion. Okay? The iron is reacting with things in the environment to create iron oxide, so you no longer have iron. Iron oxide is rust, it flakes off, and it weakens the structure of whatever it is you had. Anyway, when iron rusts, we tend to have a couple of things happening. First off, it usually starts where there's already some sort of imperfection in the iron. That becomes the anode. Okay? And remember, the anode is oxidation. That's where we're losing electrons. So we're typically going from that solid metal to metal ions. These ions tend to be dissolved in water, and that's why water is associated with rust. Okay. So we get these oxidized metals, okay, that have been corroded. Really, rusting is just a redox reaction. Now, it's also a very slow process, at least for most things, because, well, you're usually working with a few drops of water here and there. Obviously, if you have something in water, that's going to speed the corrosion process. It will also speed the process if you have water which is rich in electrolytes, like salt water. Okay, that speeds the process. Anyway, if you have something made of iron, you probably don't want it to disappear because of rust. So we have several different ways that we can prevent this corrosion. One of the easiest is to coat it with paint. So if you have paint covering all of the iron, well, the water can't get to the iron in order to have this reaction happen. It's going to prevent corrosion. A lot of bridges are painted with anti-corrosion paint. The problem is this process has to be kept up. Okay? Um, it has to, like with large bridges, it can be a constant, full-time job where people are just repainting all the time in order to prevent this corrosion. So, another thing that we can do, and this will often happen with things like ships, okay? So we've got this steel ship. So we've got a lot of iron there, and iron obviously can rust. But what we can do actually, it's kind of interesting. If we take blocks of other metals, common ones would be magnesium, aluminum, and titanium. So we just stick them right to that ship, the hull of the ship that's in contact with the water. Those metals are more likely to oxidize than the iron. And so just by putting those blocks of metals in contact with the iron, well, they oxidize instead of the iron. Now they do get used up in this process. They get used up. So that's why they're called sacrificial, because we're sacrificing them. But we would rather keep replacing these blocks in order to prevent the hull of the ship from rusting away. So we use this process, or this technique, I should say, in some other places. The book gives the example of underground pipes. Okay? We can attach a magnesium bar to it. It becomes what is oxidized instead of the pipe. Also in water heaters. Okay? If you have a big tank of water, obviously there's going to be some possible corrosion there. And so we have these long bars of a sacrificial piece of metal that get put inside of them, and they do get used up. Now, if you are paying attention, you can replace these sacrificial pieces and extend the life. If you're not, well, once they get used up, then the steel tank starts to erode away, and eventually your water heater fails. So, anyway, the third way that the book talks about preventing corrosion is a process called galvanization. Galvanization. And basically, as it says, galvanization it's a lot like painting, except instead of painting something, we dip this object in molten zinc. Or we can use a process called electroplating. We haven't talked about that yet. We'll talk about that next time. But basically, we're taking iron and we're coating it in zinc. Because zinc zinc can oxidize, but the interesting thing is, as zinc oxidizes, instead of flaking off like rust, it actually forms a protective coating. So if you've ever held a piece of zinc, probably what you were actually touching was zinc oxide, because it forms this oxide around it and provides a protective coating. And then it stops oxidizing and it's safe there. Okay. as long as the zinc coating is intact, this zinc oxide on the outside is going to prevent water from getting to the iron underneath. Okay. If, however, the zinc gets damaged, the zinc will then start to act as the sacrificial anode. And so it will oxidize before the iron object that it's protecting. So galvanization protects in two different ways. First, it's a physical barrier. And second, it is a chemical sacrificial anode. So that's section 2, right? Batteries and then corrosion. So like I said, not really math today, more conceptual and things like that. We'll stop there. We will get into section 3 next time. We do have a short homework assignment. Also, just a reminder, upcoming test, the study guide is on LMS. So. That is the homework assignment for today. Once again, in chapter 20.